तो एक बार मुझे थोड़ा बता दो कि माइक की है ना।
माइक यही इसके इनबिल्ट माइक।
अरे इसका कुछ नहीं है ना। और ये माउस अभी स्टार्ट नहीं हुआ ना लेक्चर। अभी लेक्चर स्टार्ट करने के लिए क्या है?
तो वी कैन स्टार्ट।
नहीं लेकिन क्या क्या है इसमें एक बार मेरे को जरा बता देंगे क्या?
So this is your voice.
हाँ हाँ।
Inbuilt mic is on.
हम्म।
आप ऐसे नहीं क्लिक कीजिए सर एक बार माउस पे क्लिक कीजिए।
और एक रुको पहले
फॉर नेक्स्ट स्लाइड।
एक बार ये भी करने दो इसको। ये जब पॉइंटर करना, पॉइंटर ऑप्शन, लेजर पॉइंटर ना। अच्छा अभी इसको
Now we can start.
हाउ टू स्टार्ट? टेल मी जब स्टार्ट हो जाएगा तो। Hello, good afternoon to all. My name is A.K. Chauhan, and I will be taking the last part of this advanced materials chemistry course, that is device-worthy materials. So, as you can see, in most of the devices, semiconductor materials are used. So, it is very essential to first learn some basics about the semiconductors, and then we will go ahead slowly about the other parts. So, as far as the course is concerned, this part is having actually device-worthy materials, and that is important elemental and compound semiconductors, germanium, silicon, tellurium, second, sixth, third, fifth, and fourth, sixth, and amorphous silicon. Single crystal growth techniques, Blood-Joule, Chakrovsky, hydrothermal growth of this will some growth part also we will see, and then we will see how the wafers are prepared. Crystal growth of quartz material, thin film deposition techniques, those part we will see. But before that, we will see the solar cells and thermoelectric paths and fundamentals of semiconductor physics. And so, because that is absolutely necessary to understand uh, uh, the fundamentals of semiconductor in order to understand the full functional working devices. So let us start. First, what are the semiconductors? So if we can see, all the solid state materials can be grouped into three classes. These are semiconductors, conductors, and insulators. So conductor are those materials in a crude way which conduct electricity, and those materials which does not conduct electricity are called as an insulator. Semiconductors are materials which have a conductivity between conductors and the insulators, somewhere in between. So typical electrical conductivities of some important materials in like all these three classes, that is conductors, insulators, and semiconductors are shown in this figure. So if you see the resistivity, resistivity is actually opposite of conductivity, and you must have heard the word resistance. Resistivity is related to the resistance. We can see the resistance, value of resistance is, it depends on the material, size of the material, and uh, other things like diameter, length, and all those things. But resistivity is a constant with, value for a individual material, which is actually, you can say, size independent. It is basically a resistance of standard 1 centimeter diameter and 1 centimeter length material. So if we see this side, they are very good conductors: silver, copper, aluminum, platinum, bismuth. These are good conducting materials. On the other side, we have insulators. These are glass, nickel oxide, diamond, sulfur, fused parts. And in between those, there lies the value of resistivity between 10 to the power minus 3 to 10 to the power somewhere around the 5. These materials are classified as the semiconductors. Now, what is electrical conductivity? The electrical conductivity is a result of movement of electrically charged particles. In a substance, movement of the free electrons causes conductivity. When we say charged particles, normally in liquid we can have ions also, but in solid states we have free electrons, and movement of these free electrons causes conductivity. These free electrons move under the influence of electric field, because once you apply electric field, then only an electron experiences a force towards that. Uh, so now, can a pure atom behaves as a conductor? Let us try to understand it, because pure atom, uh, if you see, pure atom does not have any free electrons. All the electrons of an atom are bound to its, you can say, nucleus. So there are no free electrons. So pure atoms cannot be conductor. But if we can remove somehow an electron from the outermost orbit or from any other inner orbits, then and free electrons are available, then we can make it to be conducting. So so there are now we realize there are two important parameters. One is the availability of electrons, and next is their capability of movement. Uh, if they can move from one place to another place, then these are two actually parameters which defines the conductivity of a material. So before we move ahead, can an electron attain all possible energies? Uh, See, if you have an electron, if an electron is a free electron, which is a plane wave also, then it can have all the possible energies. The energy spectrum for a free electron, it can have all the possible energies, it's a continuous kind of thing. But when this electron is actually subjected, this free electron is subjected to the a periodic potential. In that case, if you solve the movement of, you can say, this uh, electron, then there are only certain energy levels which are feasible. So then in that case, it cannot have all the energy levels, and So in a periodic potential, an electron will have certain discrete energy levels, and this can have only those levels. It cannot have all the levels. So now we have little bit of idea that electron, the conductivity is because of the movement of electrons only, and electrons can move under an electric field. It can take any amount of energy in case of if it is the electron is free, but if electron is not free or it is under a you can say certain potential, then it cannot have all energies. There are certain discrete energies are allowed only. So if we now see semiconductor materials, this table it shows a part of the periodic table which is related to the semiconductor materials. So normally, if we see elemental semiconductors, these are silicon and germanium, two materials which are elemental semiconductors, and these are also then there are some other uh, materials also which can be the combination of other combination of elements which can also give you semiconductor properties. So now these two materials, silicon and germanium, which are most common materials. Silicon is actually uh, be- because it is available in abundance on the earth. So this is the most you can say common material used as a semiconductor. Device gate silicon cost much less than any other semiconductor material, and silicon in the form of silica and silicates are in abundance, and it comprises about 25% of the earth crust. So it is available in abundance. And therefore, silicon is one of the most studied element in the periodic table, and silicon technology is by far the most advanced among all semiconductor technologies. Now, one was the elemental semiconductors, which were mostly silicon and germanium, but then there are compound semiconductor also. So a number of compound semiconductors have found applications for various devices. A binary compound semiconductor is a combination of two elements from periodic tables, usually one from this side, another from this side. A binary compound semiconductor is, it can be like gallium arsenide. One is, this side is, you can have gallium, this side you can take arsenic. So gallium arsenide, aluminum phosphide, indium antimonide. In a same way, you can have like different combinations. So if we can have uh, two elements, one from this side, one from this side, then this is called as the binary compound. So there are several binary compounds: silicon carbide, aluminum phosphide, aluminum arsenide, aluminum antimonide. These are the like binary compounds. So we have so many binary compounds. These are third, fifth binary compound, second, sixth binary compound, and fourth, sixth binary compound. Then we have ternary compounds also, in which you have uh, three elements, and mostly actually it was from two element only, but one element was replaced from another element of the same group with a little fraction. Suppose you have in here aluminum, gallium arsenide. So it was basically gallium arsenide, and in gallium arsenide, some fraction of gallium has been replaced by aluminum. So ultimately it becomes ternary compound. So there are some ternary compounds also. We have some quaternary compounds also: aluminum, gallium, arsenic, antimony. So so we have ternary compounds, we have quaternary compounds also, we have binary compounds also. So these are different kind of combination, and mostly all of them are made by utilizing these yellow marked elements. Most of them. There are some other also, but majority of these are from this yellow marks. So many of the compound semiconductor have electrical and optical properties that are different from those of the silicon. if we say in the compound semiconductor form. Now, one thing is we understood that semiconductor materials are single crystals where atoms are arranged in the three-dimensional periodic fashion. This periodic arrangement of atom in a crystal is called lattice. In a crystal, the atoms are at fixed positions. The thermal vibrations associated with the atoms are centered around this fixed position. In the lattice diagrams, the lattice points as dot are placed where whole structure repeats by translation. So, actually, these semiconductor materials are usually utilized in the crystalline form. And what is crystal structure? Is crystal structure, you have a lattice, and then at each lattice point, the lattice is actually lattice is a lattice is an infinite array of points which actually hold a periodicity. Means uh, you can have all the time at any point, if you reach on a lattice, you will see the identical surroundings. So all the time each lattice, then in that case each lattice point must have a translational periodicity. So if we say a translation vector T, which is suppose you have A, B, C lattice parameters, then U1, U2, U3 are like, if you say this T is equal to U1A plus U2B plus U3C, this will be I can say translation vector. These are the U1, U2, U3 are integer values. So you have crystal of a semiconducting materials which is utilized in the device. So formation of a crystal is very important. So if we see some basic crystal structures, there are actually 7 crystal systems. These are cubic, tetragonal, orthorhombic, rhomboidal, monoclinic, triclinic, and hexagonal. And there are 14 Bravais lattices. So crystal lattices, uh, they are actually as a result of translational and rotational symmetries. In three-dimensional crystals, these symmetries operation yield 14 distinct lattice types, which are called as the Bravais lattice. For a given crystal, there is a unit cell that is representative of the entire lattice. So a unit cell is, if you keep on repeating the, you can actually generate the entire lattice. The unit cell is a smallest volume which can generate your entire lattice. So these crystals mostly for our interest, when we are talking about the semiconductor materials, uh, they are specific structures. They are very, you can say silicon, which is a very common material, gallium arsenide, which is a very common semiconducting material. And if we see majority of the devices utilize these materials, so it is very, very important to just to understand the crystal structure of these materials. Crystal structure is specific or very special of these materials. So this is form of a cubic lattice. Let us first see what is cubic lattice. Cubic lattice is where the points are actually spaced in a space where your translational vectors A, B, C are same. So this distance, and this distance are same. So you will get a means the primitive can say cell will be a cubic cell where this A, B, C are same constant and at 90 degree to each other. So in cubic there can be 3 type of Bravais lattice. One is a simple cubic where 8 atoms. Suppose I consider this sphere as an atom. So there are 8 atoms which are fixed at 8 corners of the cube. And so each atom is actually 1/8 of the atom is to this cell, and remaining 7/8 is you can say given to the other cells, because there will be for each point you will see there will be 8 cells, 8 similar cubes, which will be each point will be shared by such 8 cells. So if we see simple cubic, in that case, there are this is structure. Then there is another structure of body-centered cubic where atoms are there at each corner, and there is one atom which is at the center of body. So this structure is called as the body-centered structure, body-centered cubic. Similarly, we have another structure which is the most important structure here is face-centered cubic structure. Here, atoms are fixed at all the corners as it was in this other simple cubic BCC also. And then in place of the body center, you have atoms at the all faces of the this cube. So you have now 1, 2, 3, 4, 5, 6, 7, 8, 8 atoms at 8 corners plus 1, 2, 3, 4, 5, 6, 6 atoms at the 6 these surfaces. So this atom is shared by this cube as half, and this is by 1/8. So FCC will be having 3 plus 1. So there will be 4 atoms per unit cell. In BCC, there will be 2 atoms per unit cell. So a simple cubic has 1 atom at each corner of cubic. This I have already explained. So some materials like polonium, it's a very small amount of materials which crystallize in simple cubic structure. So polonium is one such material. In body-centered crystal, there are some there are a lot of atoms, but which crystallize in BCC, but they are less than FCC. Sodium and tungsten, these crystallize here, but large number of elements they exhibit the FCC lattice from. It includes aluminum, copper, gold, platinum, and majority of the you can say metals, they crystallize in FCC structure. So FCC structure, why FCC structure is important? Because number one, this is a closed spec structure. When a material try to crystallize, suppose we consider all the atoms in form of a sphere, and let us consider that it is a single element material. So there are spheres. When this the energy is reduced, in that case all the spheres should be closely packed, because that is the minimum energy structure. So you have spheres, uh, all these spheres which were actually randomly with at high energy states, like in liquid or in gaseous state, they were having very high energy. So they were moving with a very large speed, but when they lose all their energy at the minimum energy state, they are supposed to be sitting very close to each other. In ideal situation, actually, that should be having the closest packing form. So suppose we have some atoms. These atoms have lost all their energy. Now they want to crystallize. So they will come in the closest form. So one layer has come like this. Now suppose we want to another layer, we want to put another layer of these atoms over this in the closest fashion. Then what we can do, we can put that sphere here at this point, another sphere at this point, another sphere at this point, another sphere at this point, this point, this point, and this point. If in this way we can keep on making this structure, and so we can have closed closely packed structure. So now same thing is shown here. This is one layer. Another layer is where in this group we have put the black color spheres, and now when you want to put a third layer over this layer, in that case you can see there are two possibilities. You can put the sphere here exactly above the sphere which was in the first layer, or you can put the sphere at the third layer. So now if you put the sphere at the uh, uh, in a third layer fashion, like a C layer, in that case what you form is a FCC structure. So you have one layer, then you have another layer, then you have third layer. So this structure is ABC, ABC, ABC kind of structure. This structure is FCC structure, which is the closest structure. And now if we try to see that this is actually spheres we are putting over each other, but as far as the FCC lattice was concerned, it was like this: one, two. There was eight atoms at 8 corners and 6 atoms at the 6 faces. So, but how to actually visualize this closed packed structure into FCC form? FCC should be like this. Now you have 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6. Similarly, I have put two different unit cell, one over the other. And now just in a tilted way, if you see, so the structure is like this: 1, 2, 3, 4, 5, 6 at center. See, you see this is actually what we were seeing here. So this is 6 here, and then above that this layer, and then top one is here. So this one, and then you can see. So this is the FCC is closed packed structure, and these materials which we are trying to study, or most of these materials which are used as the semiconducting here, they follow the FCC structure in a slightly we can say reformed way. What is that? That is the diamond structure. So just now we saw face-centered cubic structure, face-centered cubic structure. Now we want to study the diamond structure. Why diamond structure is important is because silicon and germanium, both these materials crystallize in the diamond structure. Now, what way diamond structure is different than other structures? Actually, it is a face-centered cubic structure only, but with slight modifications. If we see diamond, this is a diamond structure where the carbon atoms are available at 8 corners, and then at the 6 faces, 1, 2, 3, 4, 5, and 6. So at 6 faces, and then there are some extra atoms. These extra atoms are here. One is this, then another is this, then one is this, and then there is this one. So you have actually a face centered cubic, and then some extra atoms inside that. A diamond structure can also be visualized as a two interpenetrating FCC structures, where one FCC is at the 0, 0, 0, and another FCC is at diagonally 1/4, 1/4, 1/4 lattice parameters away. So you have one FCC. Just imagine you have an FCC structure and you have another FCC structure, identical structure, and you have just inserted that structure inside the first structure, diagonally moving the origin 2 1 by 4 1 by 4 1 by 4. Or you can visualize in another way. So you have only FCC structure with a basis of one atom at 0 0 0 and another atom at 1 by 4 1 by 4 1 by 4. So you can, in place of putting one carbon atom at every FCC point, you just keep on putting one at 0 0 0 and then diagonally 1 by 4 1 by 4 1 by 4 away another point. So then if you keep on repeating this structure, you will get a diamond structure. Now that is when you try to put this actually, when you try to insert extra atom in an FCC structure, which were ideally a very closed structure. We saw just 2 slides before that it is FCC was a closed pack structure. So when it was a closed pack structure, in that case, how you will be inserting extra atoms in between 2 layers? Will there not be a strain? Yes. So if I try to explain that in this picture, so you had actually, there was one layer. This was from the bottom sheet. Suppose these 3 spheres are from the bottom sheet, and I have put another atom which is at the from the top sheet. So now what I am saying actually is that I want to insert another atom in between these 4 atoms. So just imagine a situation where the exactly identical atom you are inserting between these, you can say this or you're putting at this tetrahedral void. So what will happen? This atom, this sphere will move slightly toward this side, this atom slightly this side, this atom slightly this side. There will be one atom or one sphere in between, and then you will have another sphere at the top. So this will become a structure, different kind of structure. What we are trying to see. If we try to see in this planar way, so you will have 0 0 0 0 originally at this carbon atom. Then at half, you will have the carbon atoms. At the bottom here, you will have the carbon atom. At the top also, you will have the carbon atom. And at 1 by 4 and 1 by 4, you will have another carbon atom, which is extra from this FCC. And then at 3 by 4, this you will have another carbon atom. So this is by this way, you can get the diamond structure. Why we are trying to understand this structure? Because all the as I already said you, silicon and germanium crystallize in this form, and if you want to make calculations for this structure, you will have to thoroughly understand that. So diamond lattice consists of 2 interpenetrating FCC lattices. One, this I have already explained. So it is not a Bravais lattice. There are 8 atoms in a unit cell. Each atom bonds covalently to the 4 other equally spaced about a given atom. As I said, it is like 3 sphere, and you have put another sphere over there, and then in between those spheres you have inserted another sphere. And if you will visualize, you can see that this structure is this structure can continue over the entire space in the diamond structure. So carbon, silicon, germanium, tin, all these crystallize in this structure. For diamond, the lattice parameter is 3.57 angstrom, because it is it represents in the cubic format or cubic form. So cubic is has A, B, C equal, and angle is also 90 degrees. So you can characterize by only one parameter, that is A, that is lattice parameter. For diamond, it is 3.57 angstrom, and for silicon, it is the longer one. It is slightly larger. It is 5.43 angstrom. So just to differentiate between FCC and diamond, you see, if you remove this enclosure or something on atom which is inside this enclosure, then what you get is only FCC. So you have an FCC, and in addition to that, you have something, an atom which is inside that enclosure and fixed in between the upper and this plane and this plane. This is the difference between a diamond structure and the FCC structure. So always keep it in mind that diamond structure is FCC structure only, but with an extra atom, or you can say when the atom is or the basis consists of two atoms, 0, 0, 0 and 1, 4, 1, 4, 1, 4. Now there is another very important structure for semiconductor materials. This is zinc blende structure. So zinc blende structure is why it names zinc blend. It is because the compound which was initially actually you can say studied to have this structure was zinc sulfide. That's why this structure is called as zinc blende structure. Why it is important? Because the another material, gallium arsenide, which is the another important semiconductor, direct band gap semiconductor, uh, that crystallize in this form. So what is the difference between this structure and the structure of you can say diamond structure? There's only small difference that in the diamond structure, there was two interpenetrating FCCs where both the atoms were same. So it was in the first lattice also, it was a carbon atom. In the second lattice also, it was a carbon atom. In zinc blende structure, though they are just imagine it as a two interpenetrating FCC structures. In one structure, you have one element, and on the other, you can say points, you have another element. So it has equal number of zinc and sulfur ions distributed over I just explaining this in the same way, diamond blende. So that each has four of the opposite kinds as the nearest neighbors. This structure is an example of a lattice with a basis of two types of atoms: gallium arsenide, gallium antimonide, indium arsenide, silver iodide, etc. All these crystallize in this structure. So what was the difference between this structure and the difference between this structure and the diamond structure was that when you are putting the second lattice, the atom is different than the first one. So now if we try to imagine the same example where we had three spheres and we had there was another fourth sphere above that. Now in between those four spheres, there was a space actually. So it is very easy if you try to put a smaller atom in at this void. So like in gallium arsenide, one atom is bigger, another atom is smaller. So it is a you can say comfortable fitting in such cases. So if we just try to compare between diamond and zinc blende structure, these two are technologically important structures because many common semiconductors have diamond or zinc blende structures. They share the same geometry, FCC. In both structures, the atoms are all tetrahedrally coordinated. That is, atom has four nearest neighbors. In both structures, the basis set consists of two atoms. In diamond structure, they are identical atoms. In zinc blende structure, they are different atoms. In both structures, the primitive lattice is face-centered cubic. And in both the diamond and zinc blende lattice, there are two atoms per FCC lattice points. However, as I said many times, in diamond, these two atoms are same. In zinc blende, these two atoms are different. We have been studying these two structures for a long time because these two structures uh, are these two structures because silicon and gallium arsenide crystallize in these two structures and other important semiconductors. Now, when we want to make a device, the material or the crystal, it has to be, you can say, it has to be cut in a certain direction because uh, there are different directions has different properties. So now let us understand what are crystal planes and what are Miller indices, which gives you an information about the crystal planes. Within a crystal lattice, it is possible to identify set of equally spaced parallel planes. These are called as the lattice planes. Now, how many lattice planes are possible? Ideally, there are infinite lattice planes are possible because there are infinite lattice points. So, any three lattice point, any different three distinct lattice points can make a lattice plane. The atomic spacing is different for two planes. Therefore, the crystal properties along different planes may be different. So, the crystal properties, the device properties, many device properties are actually direction dependent. So, because the interplanar spacing in different direction is different. The electrical and other device characteristics can be dependent on the crystal orientation. A convenient method of defining the various planes in a crystal is to use Miller indices. How to use, how to define using the Miller indices? Find the intercept. Now, suppose you have a plane, then imagine a like XYZ coordinate system. It will be cutting somewhere this XYZ coordinates is I can say axis. So we find the intercepts of the plane on the three Cartesian coordinates in terms of lattice constants. Now take the reciprocal of these numbers and reduce them to the smallest three integers having the same ratio. And then enclose the result in parenthesis HKL, and then this will be given as this will be said as the Miller indices of a single plane. Just to see an example, suppose we have a plane. This is a plane, and this is these are my X, Y, Z axis. So this plane is actually cutting my axis. Here it is cutting at 3A. Here it is cutting at A. Here it is cutting at 2A. So what was the first step? Find out the intercept in the form of lattice parameter. So lattice parameter is A. So it will be 3, 1, 2. So 3A, 2A and A. So now you have 1 by just reciprocal, just make a reciprocal of it. So it will be now 1 by 3. This is 1 by 3. This is 1 by 2 and this is 1. Then to make it integer, simple integers, multiply all by all with will 6. So you now you will have 2, 3, and 6. So the plane, this plane will be referred as the 236 plane. So now you have an idea of the crystal structure, you have idea of the diamond structure, zinc blende structure, you know how the planes are defined. Let us try to see another thing, which is valence bond. Um, I- all these things I am talking for the semiconductor materials perspective only. So each atom in a diamond lattice is surrounded by 4 nearest neighbors. So this is, you can say this is a tetrahedron bond because we saw there were 3 spheres and we have inserted an extra sphere in between those 3 spheres. So now this center point you have, and this is having a valency of 4 only. So all these 4, you can say 3 spheres bottom and 1 sphere top, and you have in between another sphere. So all the 4 atoms, or you can say 4 electrons of this outermost orbit will be shared by these 4 spheres or atoms. So a 2-dimensional bonding, if you see only, this is for 3 dimensions. You have 1, 2, 3, 4, and here you have like silicon, 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 silicon. So all these, like silicon has 4 electrons in this outermost orbit, and this silicon is also having 4 electrons in the outermost orbit. So all these 4 electrons will make covalent bonds, and there will not be any free electron. So each atom has this. This is from the basic chemistry, and all of you must be knowing this. The sharing of electron is covalence bonding. So gallium arsenide crystallized in a zinc blende lattice, which also had tetrahedral bonds. The major bonding force is also due to covalent bonding with a gallium and arsenic. However, in silicon, it is between silicon and silicon. In case of germanium, it is between germanium atoms. So now, when all the electrons have made bonds, uh, there are no free electrons are available. So how conduction is possible? So ideally, if you see for a semiconducting material at absolutely 0 Kelvin, it will behave like an insulator because there will not be any electron available for the conduction. As we saw in the beginning that in order to have conduction uh, of electrons, you need to have free electrons first. Now in case of all these materials, be it gallium arsenide, because in gallium arsenide also it is a 3-5, so one extra electron has been, one extra electron which was from 5 element, from the 5th group has been taken by the 3rd group. So there also there is no free electron. In silicon also there is no free electron. So then how conduction will actually take place? So at 0 Kelvin, there is no chance because all electrons are, you can say they are bonded to their respective atoms. As soon as temperature increases, so a slight amount of thermal energy can, we can say, remove one electron from this bond, and this electron can take part in the conduction. So if a bond is broken, a free electron can be released, and this free electron can participate in the current conduction. But the number of free electrons will be very, very less. It actually depends on the, you can say it is proportional to the temperature following the Maxwell-Boltzmann statistics. So at as you go on increasing the temperature, the number of free electrons will go on increasing exponentially. Now let us see what are energy bands. For an isolated atom. Now let us imagine we forget this silicon is crystallized in this crystal structure. We had a individual silicon atom, or we have any individual atom. Let us say hydrogen atom for the most simple you can say structure. So for an isolated atom, the electron can have discrete energy levels. For example, the energy levels for an isolated hydrogen atom are given by Bohr model. This is the energy level EH, which can be given by M0 Q4 divided by 8 epsilon naught square H square N square. If you solve all these things, it will come like 13.6 divided by N square. So the first energy level will be 13.6 divided by 1. The second will be divided by 4. So go on. So this way it can have discrete electronic levels. So discrete energies for n is equal to 1, 13.6. For n is equal to 2, 3.4. For n is equal to 3, 1.51, and this. So there are different only this kind of possible. Now let us consider two identical atoms. When they are far apart, the allowed energy levels for a given principal. When let us consider now two atoms. They are apart. Two hydrogen atom or two atoms, they are apart. So the energy level for this will be exactly same. Suppose 13.6 minus 3.4 minus 1.51, 0.85 and so on. But when we try to bring them together, the energy level, you can say when their wave function overlaps, in that case, the energy level will split into two levels. So the split occurs due to the Pauli's exclusion principle, which states that no more than two electrons in a given system can reside in the same energy state at the same time. So in that case, you will have a doubly degenerate system if you have two atoms. But if you have more than two atoms, if you are trying to bring an isolated atoms, if you try to bring them together to form a solid, the orbits of the outer electrons of different atoms, they will overlap as it was overlapping in case of hydrogen in last example. So they will interact, and then this interaction will be because of the attraction and both repulsive forces. Instead of two levels, because there were two atoms which were brought together. Now we are trying to bring n separate atoms. So this will be actually splitting the levels into n separate levels. These separate, though they will be separated, but closely spaced. They are not actually, you can say, single level. There is a you can say separation between them, but the separation is small. So suppose you had an atom, when they were at a very far distance, in that case all of them were having the same energy, but as you try to bring them together, and at this point when their wave functions start to overlap, in that case their energy levels also start to degenerate. So if we come this way, then the energy levels will be splitting. So suppose this is a typical interatomic distance where an atom is crystallizing with the in a cubic structure, suppose say in a cubic structure with a parameter A, in that case you will have different, I can say, so many number of equistates energy levels in place of the single level. Now, so if n is very high, then it's almost continuous, but still closely spaced separate. This band of you can say n levels can extend over a few electron volt at the inter-atomic distance of the crystal. So now this n is very large. How large it is? Suppose we just try to visualize in form of a material, say silicon only. So silicon is having, suppose in 1 cubic centimeter, silicon will be having about 10 to the power 23 atoms, nearly 10 to the power 23 atoms. So how large it is, you can just visualize. So now the electrons can no longer be treated as belonging to their parent atoms and should be considered as a crystal as a whole. So these now the electrons which was part of a atom, now it become part of the entire crystal. So let us see formation of bands in the silicon step by step. So we have silicon atom. There are this is having 14 electrons. All 14 electrons are revolving in in first orbit 1s2, in the second orbit 2s2, 2p6, 3s2, 3p2. So this atom contains 14 electrons. Out of these 14 electrons, 10 electrons occupy the inner levels, whose orbital radius is much smaller than the interatomic separation in the crystal. So these 10 electrons which are inside, that it is much lesser than the interatomic separation, which is in the case of silicon is around 5.43 angstrom. So only 4 electrons which remains in the outside orbital, these are relatively weakly bonded and can be involved in the chemical reactions. So the 3 subcell, that is, what is that? N is equal to here 3 and L is equal to 0 for S orbital. It has 2 allowed quantum states, so it will have 2 atoms, and P will be actually having a 6, but since there are only 2 electrons are available, so 2 electrons will be occupying this P state at 0 Kelvin. So out of these 6 allowed states, 2 are there in P and 2 are there in the S state. Now, if these are as far as the ground state are concerned, when they are actually at a very far distance. So this is a situation when the distance was very far. So now I imagine n atoms, isolated silicon atoms, and I am bringing them together. So right now the distance is slightly higher. So if the distance is like very large, so in that case each silicon atom will be having its own you can say energy levels. They have not yet started interacting with each other. So in that situation you will be having 2n states because they are of 3s level. Similarly, there will be 6n states of 3p level, and out of them 2n states are occupied by electrons because only 2 electrons are available in the p state. Now when you try to bring that this silicon very close to this, now what actually I am doing, I am moving this distance I'm reducing this distance, I'm reducing this distance. So on this graph, I'll be moving towards this direction. So as 3s and 3p band grow, they may merge into single band containing 8n states. So now this, once they start interacting from this point onward, so they are splitting, they will keep on splitting, and they will keep on splitting, and a situation will arrive where actually these this expansion and this expansion, they will meet this point. So if now I will try to reduce the distance further, in that case there will be continuum. So in this situation, I will be having actually 8n states, and out of these 8n states, there will be 4n states will be occupied. What was the situation here? Just try to understand. What was the situation here? There were 2n states here, and there were 6n states here. Out of these 2n states, both 2n were occupied. Here, out of these 6n states, 2n states were occupied. Now, I have come in this situation where there are 8n states. Out of these 8n states, 4n states are actually occupied and 4n states are empty. So all these states at this point are, you can say, they can be equal states like here. Now, if I further try to reduce the distance, or I will come very close to this, in that case, uh, the this levels will further behave like this, and then they further split into two parts. So now you will have this state where 4n states are here, and you will have another state where you will have 4n states here. So in the equilibrium, you will have 4n states in the lower band and 4n states in the upper band. So at now, when the temperature is absolutely zero, in that case, what will happen? All these 4n states, because there were how many electrons were there? 4n electrons were only there. 2n electrons here and 2n electrons here. So there were 4n electrons. Now all these 4n electrons are occupying at 0 Kelvin these energy levels. And these energy levels at the, you can say here, they are totally empty. So electron occupying the lowest energy state. So all the states in the lower band now will be filled, and all the states in the upper band will be totally empty. The bottom of the conduction band is called, this is called as EC, and the top of the valence band is called as the EV. So the band energy Eg between bottom of the conduction band and the top of the valence band is this one. So this is called as the width of the forbidden energy gap. Now, just to inform you that electron, it is not possible to have any electron presence with this energy. So it can be either energy can only be either in this range, or it can be under this range. So this is the formation of energy band in silicon. So physically, the Eg value, the energy required to break a bond in the semiconductor to free an electron to the conduction band and leave a hole in the valence band. So suppose all these electrons at 0 Kelvin were in the valence band, were available in the valence band, and conduction band was totally empty. So if a electron which is having an energy which is exactly equal to EV, suppose you want to give certain amount of energy, it will not accept it because this energy is not allowed. This is the forbidden. It can accept only energy which is the minimum energy is Ts plus 1.12 electron volt. So then it can, if you give this much amount of energy, then this electron can take that energy and move into the conduction band. Now, let us also understand another important thing, that is energy momentum diagram. The energy of a free electron is E is equal to P square upon 2m. From where it comes? It comes is equal to, it comes where P is momentum, which is equal to mv, and energy is half mv square. So if you just try to play with these two equations, you will get E is equal to P square upon 2mg. Now, if you try to plot energy with, you can say P, you will get this kind of parabola because it's a P square. So it has to be symmetric about this axis, about the P axis. So, and P square is obviously parabolic figure. So in a semiconductor crystal, an electron in the conduction band is similar to the electron in being relatively free to move about move about in the crystal. So if a electron is actually in a conduction band, so in a conduction band, suppose it is at the bottom of the conduction band and the entire conduction band is empty. So now suppose you try to give little energy by applying certain amount of voltage, then the energy increase of that electron will be E delta V, whatever energy you have, whatever voltage you have increased, so E into delta V. So whether this electron, which is actually at the bottom of the conduction band, whether this electron can accept that energy. So since in conduction band, all the above energy levels, which was you can say EC plus E delta V is also available there, and it is, you can say, free. Means no other electron is occupying it. So you will give any small amount of energy, this electron will be able to accept that electron, and so if it can take that energy, then its energy will be increased and it will move. So it will behave like a free electron. So in that case, if in a conduction band, that electron will be absolutely behaving like a free electron. So if it is behaving like a free electron, though it is in a, you can say, in a crystal, but it can follow this formula, E is equal to P square upon 2m. So the periodic now, but this is as far as the uh, energy gaining is concerned. But this periodic potential nucleus is, there are several actually atoms which are you can say placed there in between those. So though it can accept that energy, it can try to move like a free electron, but since it is in a periodic potential, now this will have certain constraints. So this mass of the free electron, in that case, in order to you can say in order to make this you can say in order to make this energy momentum equation valid, we try to play with it little bit smartly, that we change this m with the effective mass. We say m as an effective mass. So if it was, you can say, if it was a free electron, then it was different. But if suppose an energy which it cannot accept, so that means it cannot move with that energy. So we can also say that in that case, the electron is having a very large mass or infinite mass. So it is the same thing which we are saying, so that our equation will remain same, but we can say the mass of electron has increased very high. So if this mass of we can replace it with the effective mass, then we can use the same equation. So the electron effective mass depends on the properties of semiconductor. It can be obtained from the second derivative of E with respect to P. If you want to find out the same Mn, we can this by solving this, we can have d2E divided by dp square and then taking the reciprocal of it. The narrower the parabola corresponding to the larger second derivative, the smaller the effective mass. So if the parabola is, I can say, like if you say here, the parabola is narrower. So what it will have? It will have a actually larger mass. So larger this second derivative. So if second derivative is larger, in that case we have the effective mass is 1 upon this. So it will be smaller the effective mass. The effective mass concept is very useful because it enables us to treat electrons in the whole, in essentially the classically charged particle. Now let us try to visualize the same thing. Suppose you have a free electron and these are the lattice points. So this free electron is moving inside a periodic potential. So if this electron is trying to move from this side to this side, so if we try to plot the potential seen by this electron while this is moving from this point to this point, we can plot that potential in this form. In a slightly better way, or you can say in a slightly approximated way, I can put it in a slightly potential well kind of thing. So it is like this. Now, if we try to solve this Schrodinger equation for this electron movement of this electron, what I get is a solution which says that mv0ba on h cross square sine alpha a divided by alpha a plus cos alpha a is equal to cos k. These things are where alpha is 2me upon h square. So now just see this solution. This solution has on the left hand side, it has a certain term. If I plot this entire function or this equation, so what I will get is this curve. So this curve is the left hand side. Now, if you see the right hand side, it is the value which is cos Ka. Cos Ka means it can have a value either plus 1, it can have a value between plus 1 and minus 1 only. But here, if you see, this value is, it is crossing above 1, it is going above 1, it is coming here also, it is coming below 1, here also it is below 1, here also it is below 1, here is also it is above 1. So that means what? During this, you can say during these values, this equation is not satisfied. So solution for these values from this point to this point, this point to this point, this point to this point, let us see, it is from this point to this point, these solutions does not actually exist because the value should be, the right hand side value is, if it is between plus 1 and minus 1, so left hand side should also be between plus 1 and minus 1 only. So if you try to plot these things, or if you try to see the earlier figure, which was actually a parabola like this, now you will not have a perfect parabola, and in place of that you will have certain breaks. So here you have a break, here you have a break, here you have a break, here you will have a break, here you will have a break. So these why these breaks are there? Because of these breaks are because this equation is not solvable at certain values, and this is why this has come, because of the periodicity of the lattice. So now you will have certain band here. This is a band. Here also this is a band, and in between these two there is a gap. Similarly, between these two there is a gap. Between these two there is a gap. So this is also this one. Then there is a gap. After this gap, then you have another band. Then there is a gap. Then you have another band. Then there is a band exists from this point to this point. Then there is a gap. Then there is another gap. So you will have the gaps, and these gaps are due to the periodicity of the lattice. And where the gaps are basically for the energy of electron. So what we did, an electron which is moving inside a periodic potential, when we solve its allowed energy levels, we got an equation, and that equation suggested us that it can have only certain values where it can fit, and for certain values this equation will not be satisfying, so there are gaps. Now let us see the energy momentum diagram. So energy momentum relationship, also called as energy band diagram. For normally the energy momentum relationship is called as the energy band diagram. So if we try to visualize EP curve in 3 dimension, it is a see, it is a very complex surface. So we put like you see here, we are showing it in one direction. This is in the different direction. But if you try to plot the same in this direction, it will be symmetric only. Because towards you can say for 100, if you put 100 only, it will be symmetric. So now I am trying to show here 100, here 111. So that's why it is not looking symmetric. Just don't get confused about this. So now you have we are showing for two different materials. One is for silicon, another is for the gallium arsenide. Here it is gallium arsenide, here it is silicon. The energy momentum relates for two different directions. If the minimum of the conduction band occurs at P is equal to 0. So if this is P is equal to 0, so if you see here, in case of gallium arsenide, the momentum is actually 0 here. So if the minimum of the conduction band occurs at P is equal to 0, this means the effective mass of the electron in every direction in that crystal is the same value. So it also indicates that electron motion is independent of the crystal direction. So if you want to see the same thing in silicon, the energy momentum diagram of silicon, here you will see for silicon, for the conduction band, minimum is not actually at P is equal to 0, but it is at a certain value, which is P is equal to Pc. However, the valence band maximum is at P is equal to 0. So, it for this direction, it is at this value. So it is silicon. If you want to make a transition of electron from this point to this point, you need to actually either you need to give this much of amount of energy, which is very high, but the band gap energy is only this much Eg. So if you want to transfer an electron inside silicon material, uh, silicon crystal, so you need to provide this much energy first, and you need to also provide change in the momentum. So when an electron makes transition from the maximum point in the valence band to the minimum point in the conduction band, it not only require this energy, but require the change in the momentum also. So this kind of materials are called as the indirect band gap materials. However, in case of gallium arsenide, if you see, the p values is 0. So transition can take place from p is equal to 0 from the bottom of the valence band to the you can say top of the valence band to the bottom of the conduction band. So with this, let us see direct and what are direct and indirect semiconductors. For gallium arsenide, the maximum in the valence band and the minimum in the conduction band occurs at the same momentum, which is at p is equal to 0. Thus, an electron making a transition from the valence band to the conduction band can do so without any change in the momentum. So gallium arsenide is called as the direct semiconductor because it does not require a change in the momentum for electron transition from the valence band to the conduction band. Same thing, if you try to apply for the silicon. For silicon, the maximum in the valence band occurred at p is equal to 0, but the minimum in the conduction band, it does not occur at p is equal to 0, but it occurs at p is equal to some other value. So therefore, when in silicon, if you want to make a transition from maximum point to the minimum point, it requires a change in the momentum. So this kind of material, the silicon is called as the indirect semiconductor. That's right. So double differentiating this P curve can provide the effective mass of the electron. That effective mass is different for both the things. Now, why this direct and indirect semiconductor are important? These are important when you require very fast transitions. Actually, these transitions are slow when because the momentum changes also need to take place. However, the transitions which are direct transitions, they are very fast. So that's why when in a laser or in a light emitting applications, gallium arsenide is more commonly used because it is a direct direct band gap semiconductor material and does not require anything. So the periodicity of lattice is different in various directions. Therefore, energy momentum relations this uh, are also different for different directions. As you can see here, in this direction it is different. In this direction it is different. If you try to plot it at 100 or you try to 110, you will have a different curve. The curve may not necessarily be like this. But if you want to have in both the directions, you can say in this side also you want to have same direction, then the curve will be symmetric. So maybe we can stop here today, and some part is left. We will try to finish it in the next lecture. If you have any question, I'm ready to answer. Today it was mostly the basics of the semiconductor physics. Any questions? I'm ready to answer. Stop sharing. Can I stop?
Oh, understood.
ठीक है If no questions, then we'll see you day after tomorrow. Thank you. Okay, bye.